Tonight, we're going to explore one of the most profound constraints on reality itself. Not a law passed by governments, not a limitation of technology, not a boundary that future engineering might someday overcome. Something deeper than any of those. A set of constraints so fundamental, so built into the fabric of existence at every scale, from the subatomic to the cosmological, that the universe cannot escape them any more than a triangle can have four sides. The universe can never be perfect, not almost perfect, not perfect in most ways with a few exceptions, never in any region, at any scale, in any era of cosmic history, genuinely, completely, unqualifiedly perfect. Not in its geometry, not in its symmetry, not in its physical constants, not in the information it stores or the processes it runs or the structures it builds, not in its stars, its atoms, its fields, or its fabric. And this is not a tragedy. That statement will take the full length of tonight to justify, because the immediate reaction to learning that the universe cannot be perfect is a kind of cosmic disappointment. We wanted it to be more. We wanted the equations to close perfectly, the symmetries to be exact, the constants to be derived rather than measured, the structure to emerge from pure mathematical necessity without leftover approximations and loose ends and unexplained coincidences. But when you trace the specific reasons why perfection is impossible, when you follow the physics from the uncertainty principle through thermodynamics, through the imperfections of symmetry, breaking through the instability of perfect structures, through the role of noise in generating complexity, you discover something extraordinary. Every single thing you have ever valued in the universe, every structure, every process, every instance of complexity or beauty or life exists precisely because the universe is not perfect. Perfection in the universe would mean emptiness, would mean silence, would mean nothing. The universe's imperfections are not flaws in the design. They are the design. 7 reasons why the universe can never be perfect, and 7 ways in which those reasons are the source of everything that exists. Before we begin, if these questions about imperfection and existence and what the laws of physics reveal about why anything is the way it is, rather than some simpler, cleaner, more symmetric alternative, are the kind of questions that pull at you, hit like, or subscribe. It costs nothing and helps us reach more minds that want to think about things like this. Now let's begin. The year is 1927. Werner Heisenberg, a 25-year-old German physicist working in Copenhagen with Niels Bohr, is working through the implications of the newly developed quantum mechanics. He has been thinking about a simple question. How precisely can you know where a particle is? The classical answer is straightforward. You can know a particle's position as precisely as your measurement allows. With better instruments, you get better precision. In principle, with a perfect instrument, you could know a particle's position exactly. Heisenberg finds this answer is wrong. Not because instruments are imperfect, because nature itself is imperfect in a way that no instrument improvement can overcome. He derives what becomes the most famous inequality in all of physics, the product of the uncertainty in a particle's position and the uncertainty in its momentum cannot be smaller than a specific quantity determined by Planck's constant divided by 4 pi. No matter how clever the experiment, no matter how sophisticated the instrument, no matter how carefully you prepare the particle state, the product of position, uncertainty, and momentum, uncertainty always meets or exceeds this minimum. This is not ignorance uncertainty. This is not the kind of uncertainty you can resolve with better information. This is ontological uncertainty. The particle does not have a precisely defined position and a precisely defined find momentum simultaneously. It is not that we cannot measure both, it is that both do not exist simultaneously. The universe is fundamentally, irreducibly, unalterably imprecise. The uncertainty principle is not a technical limitation, it is a statement about the nature of reality. The universe cannot know where its own particles are and how fast they are moving at the same time. Nature cannot be perfectly precise about its own contents, and from this irreducible imprecision, everything else follows. The first reason, quantum uncertainty, forbids perfection at the foundation. The Heisenberg uncertainty principle is the first and most fundamental reason the universe cannot be perfect, and its implications extend far beyond the position and momentum of particles. The uncertainty principle applies to every pair of conjugate variables in quantum mechanics: position and momentum, energy and time, angular momentum and angular position. In every case, the more precisely one member of the pair is defined, the less precisely the other can be. This is not a pair of things where you can improve one without affecting the other. Improving the precision of one necessarily degrades the precision of the other. The energy-time uncertainty relation is particularly consequential. It says that the shorter the time interval you consider, the more uncertain the energy of a quantum system during that interval. This is why virtual particles can appear from the vacuum and exist briefly without violating energy conservation. The energy uncertainty over a very short time interval is large enough to permit the temporary existence of particle pairs that would violate conservation if they persisted. This energy-time uncertainty is the source of the quantum vacuum activity we discussed in the previous video. It is the reason the vacuum cannot be perfectly empty. A perfectly empty vacuum would have exactly zero energy at all times, which would require perfect precision in both energy and time simultaneously. The uncertainty principle forbids this. The vacuum must fluctuate. It must be imperfect. These fluctuations are not noise to be eliminated. They are the mechanism by which particles interact. The exchange of virtual particles that carries the electromagnetic, strong and weak forces between real particles happens through virtual particles that exist because of the energy-time uncertainty. Remove the uncertainty, remove the virtual particles, remove the forces. Remove the forces, remove chemistry. Remove chemistry, remove everything. The uncertainty principle means that no wave function can be perfectly sharp, that no eigenstate of one observable is perfectly defined in terms of another, that no quantum state is perfectly precise in all measurable quantities simultaneously. Every quantum system, from a single electron to the early universe, carries within it an irreducible fuzziness, an ineradicable imprecision that is built into the nature of what it means to be a quantum system. Perfect precision would require zero Planck's constant. A universe where Planck's constant is zero would be a classical universe with particles at definite positions with definite momenta, forces transmitted instantaneously without virtual particles, fields without quantum fluctuations. And that universe would also be a universe without the quantum mechanics that makes atoms stable, without the Pauli exclusion principle that makes chemistry rich, without the quantum tunneling that allows nuclear fusion in stars, without any of the quantum phenomena that make the universe what it is. The uncertainty principle is not a regrettable imperfection in an otherwise elegant reality. It is the source of reality's richness. The fuzziness at the foundation is what makes the foundation productive. The second reason, symmetry, always breaks, and that is why anything exists. In the beginning, as physicists understand it, the universe had perfect symmetry, not perfect in all respects, but perfect in certain specific symmetries that are described by the mathematics of particle physics. At the energies of the very early universe, the electro-weak symmetry was exact. The electromagnetic force and the weak nuclear force were not separate things. They were aspects of a single unified force, described by a single unified theory, with a perfect mathematical symmetry. Every particle in the theory was related to every other particle by this symmetry. The symmetry said all particles are equal. That symmetry is broken in the universe we live in. The electromagnetic and weak forces are separate, with different strengths and ranges. The particles have different masses. The symmetry is gone. This symmetry breaking is not a damage done to the universe. It is what made the universe possible. When the electro-weak symmetry broke, as the universe cooled through the electro-weak phase transition at approximately 10 to the minus 12 seconds after the Big Bang, the Higgs field settled from zero into its current vacuum expectation value. Particles that had been massless acquired masses through their interaction with the Higgs field. The electron acquired a mass. The quarks acquired masses. The W and Z bosons acquired masses. The photon remained massless. Without symmetry breaking, without this departure from the perfect electro-weak symmetry of the early universe, atoms could not exist. Electrons without mass would not orbit nuclei in stable shells. The weak force without the symmetry-broken W and Z bosons would be a long-range force rather than the short-range force that governs nuclear decay and stellar burning. The sun could not fuse hydrogen the way it does. But the most dramatic consequence of symmetry breaking is simpler and more profound than any of these details. The very existence of matter rather than nothing depends on a symmetry imperfection. Matter and antimatter are produced in equal amounts in high-energy particle physics processes. When you collide particles at high energies in an accelerator, you always produce matter and antimatter in equal quantities. This is because the fundamental symmetry of particle physics, called CPT symmetry, says that the laws of physics are the same if you simultaneously replace every particle with its antiparticle, mirror the spatial coordinates, and reverse time. If this symmetry had been perfectly preserved in the early universe, the Big Bang would have produced exactly equal amounts of matter and antimatter. They would have annihilated each other completely. The universe would contain nothing but radiation, no atoms, no star, no planets, no life. The universe contains matter. This means the early universe had a slight asymmetry between matter and antimatter. For every billion antiparticles produced, there were 1,000,000,001 particle. The slight excess survived when everything else annihilated. Everything you can see, everything that exists as ordinary matter, is the residue of a symmetry imperfection in the first moments of cosmic history. If the universe had been perfectly symmetric between matter and antimatter, we would not exist to notice the symmetry. The imperfection of symmetry breaking is the reason matter exists. Every atom, every molecule, every star, every planet, every living thing is a monument to imperfection, to the fact that the universe's symmetries, however beautiful, did not hold perfectly, that they broke. That in breaking, they created everything. The third reason, entropy, guarantees that nothing stays perfect. Even if you somehow built something perfect, even if you found a way to create a perfectly symmetric crystal or a perfectly uniform gas or a perfectly ordered structure of any kind, the universe would not allow it to remain perfect. The second law of thermodynamics is the law of imperfection in time. It says that the entropy of a closed system never decreases, that disorder always increases or stays the same, that the future is always messier than the past. This law is statistical rather than absolute. It is not that perfect order becoming disordered is impossible in principle. It is that the overwhelmingly vast majority of possible microscopic configurations of a system correspond to disordered states, while only an extraordinarily tiny fraction correspond to ordered states. chance. The probability that a system spontaneously becomes more ordered is not zero. It is just so close to zero that it has never been observed to happen in any macroscopic system in the history of experimental science. This means perfect order is unstable. The perfectly ordered crystal acquires defects as thermal fluctuations knock atoms out of their perfect positions. The perfectly uniform gas develops density fluctuations as atoms randomly concentrate in some regions more than others. The perfectly smooth surface acquires roughness as atoms evaporate and deposit unevenly. Every perfect structure is a high mountain of entropy, surrounded by vast plains of disorder, and the only direction for it to go is down. But here is what the second law giveth, even as it taketh away. The entropy gradient, the difference between the low entropy of the past and the high entropy toward which the future moves, is the energy source for every physical process in the universe. Stars shine because they are converting the organized gravitational energy of their original gas cloud into heat and light. Life exists because organisms are using the low entropy energy of sunlight to maintain their own low entropy structures against the thermodynamic tide. A universe at maximum entropy, a universe that has reached the perfect equilibrium state of maximum disorder, is a universe where nothing happens. No stars, no chemistry, no life, no thought, no movement, no change. Perfect equilibrium is perfect stasis. The perfectly disordered universe is as perfectly lifeless as the perfectly ordered one. Life and complexity and change exist in the gradient between perfect order and perfect disorder. They exist in the middle, in the imperfect region where entropy is increasing but has not yet reached its maximum. In the region of productive imperfection, the universe is currently in this gradient. The Big Bang established an extremely low entropy initial state. The heat death will establish an extremely high entropy final state. In between, for a cosmologically brief but experientially enormous span of time, the entropy gradient drives physics, drives chemistry, drives weather and geology and biology, drives thought. We are the product of an imperfect universe caught in the process of becoming more imperfect. The imperfection is not incidental to our existence. The imperfection and the existence are the same thing. The fourth reason: perfect structures are mechanically unstable. This is a discovery that comes not from quantum mechanics or thermodynamics, but from classical mechanics and structural engineering, and its implications are profound at every scale from atoms to galaxies. In classical mechanics, a system in a state of perfect equilibrium is either stable, unstable, or neutral. Stable equilibrium is like a ball at the bottom of a bowl. Push it slightly and it returns. Unstable equilibrium is like a ball balanced on top of a hill. Push it slightly and it rolls away. Neutral equilibrium is like a ball on a perfectly flat surface. Push it slightly and it stays where you leave it. The most perfectly symmetric equilibria are frequently unstable. A perfectly vertical pencil balanced on its tip is in equilibrium, but the equilibrium is unstable. Any infinitesimal perturbation, any quantum fluctuation in the position of the atoms, any vibration from the environment will cause the pencil to fall. The perfectly balanced pencil never actually balances because the uncertainty principle guarantees that there is always a small perturbation, always a deviation from perfect balance, always an imperfection that breaks the symmetry of the balanced state. This instability of perfect symmetric equilibria applies throughout physics. In particle physics, when you write down a theory with a perfectly symmetric potential and then ask what state the system will be in, the symmetric state is frequently unstable. The system rolls away from the symmetric point and settles into an asymmetric minimum. This is the mathematical mechanism of spontaneous symmetry breaking, the same mechanism that drives the Higgs field away from zero and gives particles their masses. Perfect symmetry means balanced forces with no preferred direction. No preferred direction means no net force. No net force means the system stays where it is. But if the symmetric state is a maximum of potential energy rather than a minimum, then any fluctuation away from symmetry is energetically favorable, and the system spontaneously falls away from the perfect symmetric state into an asymmetric minimum. The universe does this everywhere. A perfectly uniform cloud of gas with exactly the same density at every point is gravitationally unstable. Any tiny density fluctuation is energetically favorable. The slightly denser region has more self-gravity than the surrounding gas. Gravity amplifies the fluctuation. The gas clumps, stars form. If the primordial gas of the early universe had been perfectly uniform, with not even the quantum fluctuations that inflation stretched to cosmic scales providing density variations, there would have been no gravitational instability, no density fluctuations to amplify, no stars, no galaxies, no cosmic web, nothing. The quantum fluctuations of the inflationary era, microscopic imperfections in an otherwise smooth quantum field, were stretched by inflation to macroscopic scales. They became the seeds of every structure in the universe, every galaxy cluster, every filament and void in the cosmic web traces back to a quantum imperfection in the smooth inflaton field. The universe is structured because the inflaton field was imperfect. The structure emerged from the imperfection. Perfect uniformity is sterile. Perfect symmetry is unstable. The universe's departure from perfect uniformity in the first fraction of a second is the reason there is anything to see in any direction. Let's step back from the physics for a moment and think about what imperfection means at the human scale. The Voyager spacecraft, whose extraordinary journeys we have traced through this series of videos, were not perfectly built. They could not be. No instrument is perfectly calibrated. No trajectory is perfectly computed. No material is perfectly uniform. The computers that controlled them, with 68 kilobytes of memory and processors that would be laughably primitive by modern standards, were imperfect tools making imperfect calculations and sending imperfect commands. And yet they worked. They worked extraordinarily well. They flew by Jupiter, Saturn, Uranus, and Neptune. Each encounter precisely calculated and executed with the technology of the 1970s, with instruments designed using slide rules and early computers, built by human hands that are themselves imperfect biological structures. The engineers who built Voyager did not need perfect instruments. They needed instruments precise enough, calculations accurate enough, trajectories close enough to the ideal. The science done by Voyager is not compromised by the imperfections in its construction. It is enabled by the knowledge of those imperfections. The team knew where the instrument's calibration was uncertain. They built error estimates into their analyses. They used the imperfect data to reach conclusions that have held up for 50 years of subsequent investigation. This is how science works, not by achieving perfection, by understanding imperfection well enough to extract signal from noise, to correct for systematic errors, to acknowledge uncertainty and work within it. The uncertainty principle prevents Voyager's instruments from being perfect. Thermodynamics ensures that the spacecraft degrades over time. Imperfect symmetries in the materials mean that its structures are not uniform at the atomic scale. And 50 years later, Voyager 1 is in interstellar space, still transmitting, still doing science, still a monument to what imperfect minds with imperfect tools can achieve when they understand their imperfections precisely enough to work within them. The universe's imperfections produced human minds capable of designing Voyager. Human minds designed Voyager. with full awareness of their own imperfections. Voyager flew through a universe of imperfect structures and imperfect forces and imperfect fields and returned data that revealed the universe's imperfections in detail we had never seen before. And every discovery, every surprise, every model that had to be revised because reality did not match prediction was a discovery of a new imperfection in our understanding. The imperfections all the way down are what make the science work, are what make the doing of science meaningful. If the universe were perfect and our understanding were perfect, there would be nothing to discover. The sixth reason: stars can only shine because they are slowly destroying themselves. This is perhaps the most poignant expression of why perfection and existence are incompatible. A star is not a perfect object. It is an imperfect balance between two forces that are trying to destroy it in opposite directions. Gravity wants to collapse it. The pressure from nuclear fusion wants to expand it. These two forces reach a temporary equilibrium that we call a main sequence star. But the equilibrium is not permanent, and it is not perfect. The equilibrium is maintained by burning. The star converts hydrogen into helium in its core, releasing the energy that provides the outward pressure that balances gravity. But this process consumes the star's fuel. Every second the sun burns, it converts approximately 600 million tons of hydrogen into helium. This has been happening for 4.6 billion years. It will continue for approximately another 5 billion years before the hydrogen in the core runs out. When the hydrogen runs out, the balance breaks. Gravity wins temporarily. The core contracts and heats. The outer layers expand. The sun becomes a red giant. Eventually, the sun will shed its outer layers, leaving behind a white dwarf, an object no longer balanced between fusion and gravity, but held up by the electron degeneracy pressure of a quantum mechanical principle that prevents electrons from sharing state. The sun's light, the light that drives photosynthesis on Earth, that powers the water cycle, that warms the surface to temperatures compatible with liquid water and life, is the product of this ongoing imperfect balance. The sun is slowly dying. The light it produces is the energy released by the process of its dying. The light that makes life possible on Earth is the exhaust from a cosmically slow explosion. If the sun were in perfect equilibrium, if the forces were perfectly balanced in a stable rather than a temporary way, it would not burn. A star in perfect thermodynamic equilibrium with its environment would emit no more light than it received. It would not be a source. It would be a background object, radiating at the same temperature as its surroundings. Stars shine because they are not in equilibrium, because they are imperfect, because the perfect balance between gravity and fusion pressure is temporary, and the star is slowly spending its fuel to maintain it. The light that made us possible is the product of imperfection and imbalance. The sun is in the middle of destroying itself so that we can exist. Its imperfection, its instability, its inexorable consumption of hydrogen that will eventually run out, is the source of every photon that has ever warmed the Earth, powered every plant that has ever grown, ultimately powered every living thing in the history of terrestrial life. Perfection would have meant no light, no warmth, no life. The fifth reason: information cannot be perfect without becoming useless. This is a deep result from information theory that most people encounter in the context of data compression or communications. but that applies throughout physics and biology. Claude Shannon, the mathematician who founded information theory in 1948, proved that the amount of information a symbol carries is directly related to its improbability. A symbol that is perfectly predictable, that always occurs in a known context, carries no information. A symbol that is completely random, that has no predictable relationship to anything, also carries no information in a practical sense, because it cannot be decoded. Information lives in the middle, in the region between perfect predictability and perfect randomness, in the region of structured imperfection. This is why language works. If words were perfectly predictable from context, you would need no words. You would already know what was coming. If words were perfectly random, each word would be uncorrelated with every other word, and no meaning could be conveyed. Language carries information because it is in between, because it has patterns and correlations that constrain but do not determine the next word, because it is imperfectly structured. This principle extends to DNA. The genetic code is not random. Random sequences of DNA would produce random proteins, most of which would fold incorrectly or not at all. Random DNA is noise, not code, but perfectly determined DNA that encodes the same protein everywhere in every context is also useless. Useful DNA is imperfectly random. It has structure, it has correlations, it has regions that are highly conserved because they encode essential functions, and regions that are highly variable because variation allows adaptation. The information in a DNA molecule, the information that encodes an organism, is possible only because the sequence is imperfect, neither maximally ordered nor maximally disordered. In the productive middle where Shannon information is maximized. Now extend this to the universe's physical laws. The laws of physics are, in a sense, the universe's information compression algorithm. They describe regularities, patterns, correlations. They allow you to predict the future from the past. They encode the structure of the universe in compact form, but if the laws were perfectly deterministic, if they left no room for imperfection, then the universe they describe would be perfectly predictable. Nothing genuinely new could happen. Every future state would be fully determined by the initial state. The universe would be, in the information theoretic sense, a program that simply runs to its predetermined conclusion without generating new information. The quantum uncertainty of the universe's laws, the fundamental indeterminism that means you can only predict probabilities rather than outcomes, means that the universe generates new information constantly. Each quantum measurement, each irreversible thermodynamic process, each moment of spontaneous symmetry breaking in a quantum system generates a new fact that was not predetermined by the earlier state of the universe. The universe creates information, not just stores it, creates it. This information creation is possible only because the universe is not perfectly deterministic, because it is, at its foundation, genuinely and irreducibly imperfect. That information creation is the source of novelty in the universe, of genuinely new structures and processes that were not contained in the initial conditions, of life, which creates new genetic information through mutation and selection, of thought, which creates new ideas that were not determined by the prior configurations of neurons, of science, which creates new understanding that was not contained in the observations that preceded it. The universe's imperfection is its creativity. The seventh reason: the constants of nature are not perfect, and that is not an accident. If you had to design a universe from scratch, using pure mathematics and requiring everything to be derived from first principles with no free parameters, you would face an impossible task. Because our universe has approximately 26 fundamental constants that cannot be derived from any more fundamental theory. They must be measured. They are what they are without deeper explanation. The mass of the electron, the mass of the proton, the strength of the electromagnetic force, the strength of gravity, the cosmological constant, the Higgs vacuum expectation value, the speed of light, Planck's constant, the fine structure constant. These numbers are the inputs to the universe's equations, not the outputs of some more fundamental theory. They are free parameters, and the values they have are not perfect in any mathematical sense. They are not round numbers. They are not simply related to each other by clean mathematical ratios. The ratio of the proton mass to the electron mass is about 1,836. The fine structure constant, which determines the strength of the electromagnetic interaction, is approximately 1/137. These are not obviously special numbers. They do not emerge from any mathematical framework that would allow you to derive them. This bothers physicists enormously. The deepest hope of fundamental physics is to find a theory that explains why the constants have the values they have. A theory of everything, a truly fundamental description of reality, would ideally predict the constants rather than treating them as inputs. String theory, the leading candidate for such a theory, has not yet achieved this. It predicts a vast landscape of possible constants with no clear mechanism for selecting which values are actually realized. But here is what we know about the constants we have. They are extraordinarily well suited for the production of complexity. Change any of them by even a small factor, and the universe becomes dramatically less hospitable for the structures we consider interesting. If the electromagnetic force were slightly stronger, electrons would be bound so tightly to nuclei that chemical reactions would be too slow for chemistry to drive biology. If it were slightly weaker, electrons would escape their nuclei and atoms would not exist. If gravity were stronger relative to electromagnetism, stars would burn out faster than planets could cool and life could develop. If the cosmological constant were larger by a factor of 100 or so, the universe would have expanded too fast for galaxies to form before their matter was diluted to negligible density. The constants are not perfect in any mathematical sense, but they are, in a very specific sense, just right for producing a universe where things happen, where structures form, where chemistry works, where stars burn for billions of years, where information processing systems of sufficient complexity to ask questions about the constants can exist. Why are they this way? There are three possible answers. The first is pure coincidence, which seems astronomically unlikely given how precisely they must be tuned for our kind of universe to exist. The second is design, which is a metaphysical claim beyond the scope of physics. The third is the anthropic principle applied to a multiverse. If the constants vary across an enormous number of universes, the only constants we can observe are those compatible with our existence. We find ourselves in a universe with these constants because only these constants permit our finding. The truth is, we do not know. The imperfection of the constants, their apparent arbitrariness, their lack of derivation from deeper principles, is one of the central mysteries of fundamental physics. It is not a solved problem. It is an open wound in our understanding, a place where the fabric of physics does not close perfectly. And yet the constants, being what they are, imperfect, not derivable, apparently arbitrary, is the source of everything we know. The imperfection of not having a perfect theoretical explanation for the constants is the price of having constants that permit the universe to be interesting. Here is where the 7 reasons come together into a single picture. The universe cannot be perfect because perfect precision would require Planck's constant to be 0, which would eliminate quantum mechanics and everything that depends on it. Perfect symmetry would require spontaneous symmetry breaking to not occur, which would leave particles massless and forces unified in ways incompatible with atoms. Perfect order would require 0 entropy generation, which would mean no thermodynamic gradients and no physical processes. Perfect stability would require all equilibria to be stable, which would leave gas clouds uniform and prevent gravitational structure formation. Perfect information would require perfect determinism, which would eliminate quantum randomness and the genuine novelty of new information generation. Perfect stars would require perfect equilibrium, which would mean no burning and no light. Perfect constants would require derivation from a deeper theory, which we do not have. And the specific imperfect constants we do have are what makes the universe hospitable to anything interesting. Remove any of these imperfections and you remove something essential. Remove all of them and you remove everything. The universe is not imperfect despite being what it is. It is what it is because it is imperfect. This is the insight that takes the longest to absorb. We come to the question of the universe's imperfection with an intuition that perfection is the standard and imperfection is the failure to meet it. That a perfect universe would be better than the one we have, and our universe falls short of the ideal. But this intuition has things backwards. The ideal of a perfect universe, a universe with exact quantum precision, exact symmetric equality of matter and antimatter, exact thermodynamic stability, exact structural uniformity, exact information determinism, exact equilibrium in every star, exact mathematical elegance in its constants. That ideal universe contains nothing, no atoms, no forces, no matter, no structure, no life, no thought. Perfection in a physical universe means emptiness. The imperfections are not the universe failing to be what it should be. They are the universe being what it needs to be anything at all. There is a deeply human dimension to this that deserves its own moment. We celebrate imperfection in art, even when we do not recognize it as such. The thing that makes a musical performance extraordinary is not the perfect execution of the notes as written. It is the slight variations from perfect tempo, the subtle dynamic shaping that goes beyond the score's instructions, the moment of genuine emotional expression that departs from the mechanical reproduction of the written music. The perfect performance of a perfect machine is not what moves people. The imperfect performance of a human musician with all the microtonal variations and expressive timing and subtle energy that no algorithm can fully reproduce is what moves people. This is not a quirk of human psychology that we would be better off correcting. It is a reflection of the same principle that governs the universe. Information lives in the imperfections. Meaning lives in the departures from the expected. The beauty of a musical performance is in the signal it carries, and that signal is in the structured imperfections, the variations that are not random but not perfectly predictable either. The same is true of language, of visual art, of human faces, of natural landscapes. The perfect face is uncanny. The perfectly manicured landscape is sterile. The perfectly regular crystal is beautiful but lifeless. The imperfect landscape, with its unexpected valleys and strange rock formations and irregular vegetation, is alive in a way the perfect landscape is not. The imperfect face, with its asymmetries and individual characteristics, is recognizable as a person in a way the perfectly symmetric averaged face is not. We respond to imperfection because we are products of imperfection. Our brains, themselves products of evolution, an inherently imperfect process of mutation and selection, are built to find information in the deviations from the expected. The signal is always in the imperfection, always in the departure from the baseline, always in the asymmetry and the variation and the noise that structured information rides on. The universe is not perfect. We are not perfect. Neither is perfect in the same way, for the same reasons, as those reasons are the reason there is a universe that contains beings capable of caring about imperfection. Let's trace the implications of universal imperfection through the specific history of the universe we know. The Big Bang established the initial conditions. Those conditions were not perfectly symmetric. As we have discussed, the slight asymmetry between matter and antimatter, 1 part in a billion, left a residue of matter when everything else annihilated. That residue is everything. The inflationary era amplified quantum fluctuations from microscopic scales to cosmic scales. Those fluctuations were not perfectly distributed. They had slight variations from region to region. Those variations were the imperfect seeds of structure. After inflation, the universe was a hot, dense plasma. It expanded and cooled. The matter in it was subject to both the gravity pulling it together and the pressure pushing it apart. The slight density variations from inflation began to grow under gravity. Dense regions attracted more matter. Less dense regions lost matter to the surrounding denser regions. Over hundreds of millions of years, the density variations grew into the first structures. Filaments of dark matter formed the cosmic web. Ordinary matter fell into the dark matter scaffolding. Gas clouds collapsed. The first stars ignited. Those first stars were not perfect. They formed from imperfectly uniform gas clouds. They were not perfectly spherical. Their nuclear reactions were not perfectly efficient. They produced heavy elements, carbon and oxygen and iron and all the rest, through nuclear processes that were not perfectly clean, that left behind neutron-rich nuclei and radioactive isotopes and complex abundance patterns. Those heavy elements were scattered by stellar deaths, by stellar winds and supernova explosions that were not perfectly symmetric, that produced asymmetric remnants and asymmetric nebulae and asymmetric abundance distributions in the interstellar medium. Second-generation stars formed from that enriched gas, imperfectly. Some formed binary or multiple systems rather than isolated stars. Some formed with planets. The planets formed from imperfectly distributed disks of gas and dust, accreting material through imperfect collisions, differentiating into cores and mantles through imperfect gravitational sorting. On at least one planet, The imperfect chemistry of the early oceans and atmosphere produced molecular systems complex enough to replicate themselves. Those systems were not perfectly faithful in their replication. They made errors. Those errors were mutations. Most mutations were harmful or neutral. Some were beneficial. The beneficial ones spread. The populations changed. Over billions of years, the imperfect replication of imperfect molecular systems produced the extraordinary diversity of life. And eventually, in at least one lineage, the imperfect information processing systems of neural tissue became complex enough to ask questions about the imperfection of the universe. To trace the sequence of imperfections from the Big Bang, through inflation, through matter formation, through star formation, through stellar nucleosynthesis, through planet formation, through the origin of life, through evolution, to the existence of minds wondering about imperfection. Every link in that chain is an imperfection, a departure from perfect symmetry, an asymmetry, a fluctuation, a mutation, an error, a noise-driven deviation from the expected. And the chain connects the Big Bang to us. The universe is not perfect. And the imperfection is the point. What does this mean for how we understand our own existence? We are the universe's imperfections looking at themselves. The asymmetry that produced matter over antimatter produced the atoms we are made of. The quantum fluctuations that seeded structure produced the galaxy and the solar system we exist in. The stellar imperfections that produced heavy elements produced the carbon and oxygen and nitrogen in our bodies. The replication errors that drove evolution produced the neural architecture that allows us to have this conversation. We are not despite the imperfections. We are the imperfections. Organized, complex, self-aware imperfections, but imperfections nonetheless. This realization changes the relationship between perfection and value. The standard intuition is that value tracks perfection. The better something is, the closer to the ideal, the more we should value it. The perfect circle is more mathematically beautiful than the wobbly one. The perfect performance is more aesthetically valuable than the flawed one. But the universe reveals that this intuition operates only locally, only within a domain where the basic conditions for existence are already established. When you ask not which of two imperfect things is better, but whether an imperfect universe or a perfect universe is better, the answer is clear. The imperfect universe contains things. The perfect universe contains nothing. Within the context of an existing universe, the pursuit of greater precision, greater symmetry, greater elegance, greater understanding is valuable and meaningful. Science is the project of understanding the universe's imperfections with increasing precision. The quest for a theory of everything, a unified description of all the constants and forces and particles, is a quest for the explanation of imperfections that currently seem arbitrary. But that quest is itself a product of imperfection. The questioning minds that pursue it are products of quantum uncertainty and symmetry breaking and thermodynamic gradients and gravitational instabilities and information-generating mutations. The science is possible because the universe that produced the scientists is imperfect in exactly the right ways. The perfection we seek in our understanding is not the elimination of imperfection from the universe. It is the perfect understanding of why the universe's imperfections are what they are. It is the complete explanation of why Planck's constant has the value it has, why the constants of nature are what they are, why the symmetries break in the specific ways they do. That perfect understanding would not reveal a perfect universe. It would reveal a universe whose specific imperfections are necessary and sufficient for the universe to be anything at all. A universe whose imperfections are not flaws but features, not defects but design. If design is the right word for a universe that is what it is for reasons we are still discovering. We began tonight with the claim that the universe can never be perfect, and that this is not a tragedy. The case for that conclusion has been made. The quantum uncertainty that makes precise knowledge impossible also makes virtual particles possible, which makes forces possible, which makes atoms possible, which makes chemistry possible, which makes us possible. The symmetry breaking that destroyed perfect symmetry also gave particles their masses and created the matter asymmetry that left matter in existence at all. The entropy law that ensures nothing stays perfect also drives the thermodynamic gradients that power every physical and biological process. The instability of perfect structures drives the gravitational collapse that forms stars and the density fluctuation growth that forms galaxies. The information-carrying capacity of imperfect systems, systems between perfect order and perfect chaos, is what makes communication and genetics and thought possible. The imperfect balance between gravity and fusion in stars produces the light that drives life. The imperfect, apparently arbitrary constants of nature are what make the universe hospitable to anything interesting. 7 reasons. 7 ways the universe cannot be perfect. 7 ways the imperfection is the point. The universe is 4.5 billion years into one star's life on a planet where imperfect chemistry eventually produced imperfect biology that eventually produced imperfect minds. Those minds built imperfect instruments and used imperfect mathematics to understand imperfectly the universe that produced them. They found the universe to be quantum mechanically uncertain and thermodynamically irreversible and structurally unstable and informationally noisy and physically asymmetric and cosmologically arbitrary in its constants. They found the universe to be irreducibly, inescapably, magnificently imperfect, and they found that the imperfection is not the obstacle to the universe being everything it is. The imperfection is the reason the universe is everything it is. Carl Sagan, whose influence we have traced through this series, wrote about the universe as something we are inside, something that produced us, something we are made of. He described us as star stuff, assembled from the imperfect nuclear furnaces of stars that died billions of years ago, from the asymmetric remnants of quantum fluctuations that were stretched to cosmic scales by inflation, from the imperfect chemistry of an early Earth that somehow, against all apparent odds, developed the capacity to know what it is made of. We are the universe noticing its own imperfections, measuring them, tracing their consequences, following the chain from quantum fluctuation to galaxy to star to planet to cell to mind, asking why the constants are what they are, asking whether the vacuum is stable, asking what the universe was like before there was anything to measure it. These questions are themselves imperfect. They are incomplete. They lead to further questions rather than final answers. The universe's imperfections generate the questions and prevent the final answers from being reached. The questions are always running slightly ahead of the answers, the way the horizon is always slightly ahead of the traveler. This is not a problem. This is the universe keeping itself interesting, keeping us searching, keeping physics alive and productive and surprising. The day we find the theory of everything, if we ever do, will be the day we understand why the universe's imperfections are what they are. That will be a day of extraordinary achievement. But the day after that, we will discover new imperfections, new departures from the expected, new structures in the data that do not quite fit the theory, new signals in the noise that suggest there is something we have not yet understood. Because the universe is imperfect, and understanding that imperfection is a project that does not end, cannot end. Because understanding the universe perfectly would require a perfect mind in a perfect universe, and perfect minds do not exist. And neither does a perfect universe. And that, at the end, is why everything does.